Thanks, Misha. It's really nice to be here. Thanks for having me. So today I'll tell you about how to look for light new particles with black holes. And Misha said that people usually ask questions during the talk, so feel free stop me and ask questions. I'm a particle theorist, and so I'll start with motivating a little bit the searches for these new particles that I'll be discussing today. The main motivations for this light new states that we'll be looking for are kind of threefold. We have many outstanding theoretical puzzles in the standard model. One of my favorites is the strong CP problem, which is a very well-defined question that I'll discuss about small parameters in the standard model. We also have the experimental proof that there is physics beyond the standard model, which is the existence of dark matter. And there's just kind of pure curiosity to try to push our understanding to higher and higher scales. And it turns out that axions can address to some extent all three of these questions. So let's talk about axions for a few minutes. So I'll be discussing both what's called the QCD axion and more general axion-like particles. The QCD axion was first proposed as a solution to the strong CP problem. So let me just tell you a bit about the strong CP problem. It's the fact that theoretically in the standard model, there's already a lot of violation of charge and parity symmetry. And but it does not appear to propagate to a particular combination of parameters in the strong interactions. If that combination were non-zero, it would, for example, give electric dipole moment to the neutron. And you can see this kind of simply for parity. For example, if you have a neutron with a spin and a dipole moment, and you do a parity transformation, the dipole moment is a vector and it flips. The spin is a pseudo vector and it flips twice, so it remains invariant. So for example, the dot product of these two quantities is not conserved under this transformation. So clearly, the observation of like electric dipole moment in a neutron would be evidence of parity violation in the strong sector. We've done measurements of this quantity and we don't see it. In particular, if you take order 1 values for these parameters, which also show up as, for example, phases in the quark mass matrix, the expected value of the electron dipole moment is about 2 times 10 to minus 16 e centimeters times this parameter theta. But in laboratory experiments, the upper bound currently is about 10 orders of magnitude smaller. So, and in fact, this theta, as I keep referring to, is actually a linear combination of 2 independent parameters in the standard model Lagrangian. So this is a large unexplained cancellation. Luckily for us, it has a very nice potential explanation, a dynamical explanation, which is to solve this problem by promoting theta to a dynamical field, which is called the axion. So if you take this theta parameter and instead say that it's a field suppressed by some high scale f, the strong interactions which couple this theta parameter to the strong sector give it a potential which kind of looks like this. And I guess I point with my mouse right. Okay, so you have this potential. If you have no axion, then this is just some parameter, and it can be anywhere on this line. But given that it's a dynamical field, it wants to relax to the minimum to minimize the potential energy, and it'll sit here at the bottom. And expanding around the minimum gives you a relationship between the mass and the scale by which the interactions of this new particle are suppressed, which for the masses I'll be talking about are roughly this. So the mass mu is 6 times 10 to minus 12 electron volts for a very high symmetry breaking scale f. So this would be much, much lighter than any particles we've seen so far. So this was proposed in the late 70s. And it was soon realized that the axion is also a potential answer to the dark matter problem. It can easily be produced in the early universe, and the axion, or actually any other light scalar or pseudoscalar field. So the cosmological evolution of the amplitude of the axion field A, which I'm showing here, is analogous to a damped harmonic oscillator, where the damping is given by Hubble friction, and the frequency is given by the mass. So in early times, when Hubble is very large in the early universe, this is a frozen harmonic oscillator. This amplitude of the field is frozen by Hubble friction. But later on, the universe expands and Hubble drops to below the mass, and the amplitude oscillates around the minimum in precisely the right way to make it redshift as cold dark matter. And if the mass is not too light, all the clumping and other properties of it are very similar to cold dark matter as well, or almost identical. So this is a great cold dark matter candidate, and you don't need to assume much about the early universe production to make this work. For a general axion-like particle, not the QCD axion, that's a little more complicated. This is what you need to get the right dark matter abundance. So the fractional energy in the axion as a function of the dark matter gives you the right value for example, for an EV axion, depending on its amplitude and initial condition. So just to put this on a plot, we have two lines here. So here's the mass of the axion in EV. To give you a sense of scale, the Compton wavelength is shown on the top axis here. So we're really looking at kind of macroscopic size particles. And this FA scale at which the axion, up to which the axion is kind of a free particle, that's where there's a broken symmetry and the axion is produced, is shown here in GeV. So the QCD axion is the green line here, where the strong CP problem is solved, so where the CP violation standard model is relaxed to a minimum. And for general axion-like particles, this blue region is where axion is dark matter for generic initial conditions. So these are interesting places in the parameter space to be looking for new particles motivated by these outstanding problems. And notice that the interaction scale of this particle, this FA, is very, very large. So we've already excluded some parameter space shown here in gray, but anywhere here, if you find this new particle and you can convince yourself that it is something like an axion, then it would immediately tell you that there's some interesting new physics happening at these very high scales, which are not accessible in laboratory experiments, for example. So that's the motivation. So axions could address strong CP problem. They could make up the dark matter of the universe, and they could also teach us high scale physics. And so we want to do our best to try to look for them. So how do we look for these particles? So as I mentioned, we already know that they're very weakly coupled. They're pseudo-Goldstone bosons. And if you look at this plot, you can immediately see that much of the current success of searches comes from stellar and neutron star constraints. That's because these particles are very weakly coupled. They're difficult to detect in the lab, although there are some great ideas for that as well. And so you need some large, very high density objects to create a reasonable enough amount of these particles to actually be able to observe their effect. So for example, for stars, for the sun in particular, you can convert a non-negligible fraction of the thermal energy of the sun to axions, and that's something that you can look for. And this is efficient because in the sun you have a lot of emission from, say, photons. Those are mostly carrying away the energy at a small volume or at the surface of the star, because photons have very short mean free paths. So even though you're producing many, many of them, you're only really emitting them at, effectively at the surface. The axions are very weakly interacting, and so you get volume emission. So even though the axions are much, much more weakly coupled than a photon, you can carry away order 1 of the thermal energy of the sun. Well, at that point, you know, these particles don't exist because we know there's nothing else carrying away order 1 of the thermal energy of the sun, but that's something that you can use to put constraints on these new particles. The goal in the main part of my talk will be to tell you a new way to take away energy from astrophysical objects, in particular black holes, to probe even more weakly coupled particles than we can with something like the sun. So to orient you, here we'll be talking about very light particles whose Compton wavelength is of order of the black hole horizon. So tens to thousands of kilometers for astrophysical black holes, and whose couplings range from those we can probe with the sun, so a few billion GeV, to basically the Planck scale, so gravitationally coupled particles. Any questions so far?
So in this plot, like I would assume like the QCD axion line would have like uncertainty because of theoretical models. And why is the dark matter axion have uncertainty?
Good. Yeah. So what are the thicknesses of the line? So in this, this plot is, you're correct, is a little bit of a cartoon. So I'm showing here. So the QCD axion line is actually a line because it's given exactly by the instanton contribution. There's some uncertainties when you try to do proper calculation, but that uncertainty is really quite small. So that's captured in the thickness of the line. The cartoon part is trying to transpose all of these other bounds onto this plot because those rely on the photon coupling and not the fundamental FA scale of the particle. And so that has model uncertainty, and I've assumed kind of a typical coupling to photons to put most of these gray bands on here. The thickness of the dark matter line, it comes from initial condition uncertainty. So within the darker region, I think I'm varying theta within. So you start on this axion potential, right? And how far away are you from 0 or from pi? If you're order 1 away from 0, you'll get the right dark matter abundance within the dark blue band. If you start to tune close to the bottom or to the top of the potential, but I think I assumed a factor of 100 to the bottom and maybe a 10 to the 4 to the top. It's harder to tune at the top, then you get a slightly broader range.
The KSVZ models, like I mean the QCD axion, I'm used to like seeing it as a band. So. Yeah,
so the band is, so that's what I'm saying. So the band is the model uncertainty and the coupling to particular standard model particles. The QCD axion itself, the relationship between MA and FA is a line, but then how it couples to say photons has some model uncertainty, and that's what you're used to seeing. Exactly. Good. Other questions? Okay, so here is where we're going. First, I'll tell you about how to extract energy from black holes using a process called black hole superradiance, and then I'll briefly talk about gravitational searches for these ultralight axions, and then I'll talk about some recent work about what happens when the axions are interacting with one another and turns these black holes into basically new sources of axions in the universe. So black hole superradiance is a particular example of a more general process called rotational superradiance. In kinematics, this is easy to see what happens if you have a cylinder like this, and it has some friction. You throw some object at it like a ball, it'll slow down because of the friction. If you have now a rotating cylinder and the ball is going slowly relative to the rotational tangential velocity of the cylinder, then actually the ball will extract energy from the cylinder rather than slowing down. So there will still be dissipation in the system, but now the dissipation is actually imparting kinetic energy to the outside, to the incoming particle, because in the frame of the cylinder, it looks like slowing down the ball actually looks like, is actually giving it more kinetic energy. So this effect is, the key is that it depends on the amount of dissipation in the system, and it also is necessary that the angular velocity is fast compared to the tangential velocity of the object. This happens also with waves and black holes. So black holes are perfect dissipators. Anything that you throw at a stationary non-rotating black hole will get absorbed with some rate. A wave scattering off a rotating object like a black hole can increase in amplitude if the black hole is rotating fast enough. So it will come in with a smaller amplitude and come out with a larger amplitude if the angular velocity of the object, in this case the horizon, is faster than the phase velocity of the wave. And so that's the superradiance condition, that the phase velocity, the energy over the angular momentum number, is small compared to the velocity, angular velocity. Unlike the ball example, here you have an increase in the number of particles or the number of modes in the wave rather than the kinetic energy. So the energy of each photon in this case, for example, would be the same, but the number of photons would increase rather than the whole, because it's a coherent process.
This is completely generic for any kind of wave. So
it is generic for any wave that has an interaction which is dissipative with the object. And they have to be bosonic waves, so you can actually amplify the number of states. So if you shoot fermions at it, you won't get a larger number of fermions in the same state. And it's also generic for other things, not necessarily black holes. So Zeldovich initially thought of this as like a rotating cylinder, which has some dissipation because of resistivity that absorbs electromagnetic waves, and it could in principle also be canceled. So this is one example of your question is what kinds of waves. You can do gravitational waves when they're scattering from a rapidly rotating black hole. So you have a blue gravitational wave coming in, and it's rescattered as a larger amplitude outgoing wave as shown in red. So this is a full numerical GR simulation done by Will East. It's cut off over there, who's a faculty at Perimeter. So you can see that the amplification is very significant here. In particular, this is related to the fact that these are spin 2 particles that are in the wave. The amplitude is increased more than for a scalar particle. So that's all very nice, but it doesn't really help us extract a lot of energy from the rotating object, because you have a wave coming in and then it gets amplified by some amount and then it goes off to infinity. It would be nice if you could somehow make this process a more runaway process. And this was proposed by Press and Tucholsky, I think in the 60s, where if you surround this black hole by a mirror, then you could have a runaway process where you start with some incoming wave. It will get amplified by the black hole, but then it'll get reflected from the mirror and it will keep getting amplified more and more. The rate at which the amplification happens is proportional to the energy density of the wave. So it becomes an exponential process, and eventually the radiation pressure inside the mirror becomes so large that the mirror explodes. So this is what they call the black hole bomb. It's not a very efficient way to try to extract energy because it's hard to get a perfectly spherical mirror around a black hole. But this does tell us that this process is possible if you can get some sort of bound states that satisfy the superradiance condition around an astrophysical black hole. Another nice point is that this is not necessarily a resonant condition, so you don't exactly have to tune the mirror to be a perfect size relative to the black hole size. You just have to trap particles kind of near the black hole to efficiently repeat this process.
When the waves have become amplified so much, then they have nonlinear interactions between.
That's great, and that will be the third part of my talk. So for now, we're going to just talk about gravitationally coupled interactions. So the nonlinearities are subdominant. And here we have particles that are trapped near the black hole just by the potential, gravitational potential. So far away from the black hole, you can think of it as a 1/r potential, which is exactly g Newton times the mass of the black hole times the mass of the particle. And if you have the wavelength of the particles of order the black hole size, then they'll form these coherent bound states that are solutions to this potential in the vicinity of the black hole. They look very much like your hydrogen atom solutions. Of course, close to the black hole, they're different, and that's very important. but most of the energy density sits in these hydrogen-like orbitals, because you're solving the same equations for a non-relativistic scalar field as you would for the hydrogen wave function. Far away again from the horizon, RG is the black hole size. The hydrogenic potential is a good approximation, and so you can solve it with the regular quantum numbers NLM, which is principal and the angular momentum numbers. And so the energy density in those states would look like this for the S, the P, and the D orbital. So you can use the intuition about the hydrogen atom to figure out what the bound states look like. I'll be referring to this alpha fine structure constant, which is just the ratio of the black hole size to the Compton wavelength of the particle. It'll be a number that's usually less than 1. So this will be a perturbative system. And it's analogous to the fine structure constant of ENM because it's the coefficient of the one over potential. The radius of these will be a few to a few hundred black hole radii. So these things are sitting close to but far outside of the black hole. And the things become interesting once the occupation number is large. So in particular, if you have many particles, as many as 10 to the 80, then you can get interesting phenomenology and observable effects. And I'll tell you in a second where that number is coming from. And of course, you need to generate. So these are just quasi-static solutions, but you need to generate them. So that comes from superradiance. You have a boundary condition at the black hole, which is the absorptive condition when the black hole is at rest. And that creates an imaginary frequency component to the energy of these particles. So you have the energy of each particle is given by the rest mass mu, with some correction for the binding energy that comes from the gravitational binding to the black hole, just like for a hydrogen atom. And then you have some imaginary frequency, which is positive or negative depending on if these bound states satisfy the superradiance condition. So if you have a quickly enough rotating black hole, then this will be a positive number for some states, and this will become an exponential runaway growth.
What mass does that occupation number correspond to?
This occupation number is for stellar mass black holes and axions that have the wavelength to give alpha of order 1, so about 10 to minus 12, 10 to minus 13 eV.
So what's the total mass of the axions?
Oh, in the cloud, it's a few percent of the black hole. Yeah.
Without derailing your talk completely, how do you calculate this capital gamma in practice?
Yes, so in practice, you can do it several ways. The way that we do it is a semi-analytic solution. You have a solution that is far away from the horizon, which are these hydrogen-like orbitals that are valid because you can, far away from the black hole, the curvature is negligible, so you can just solve the one of our equations for massive non-relativistic scalar. And you know what those solutions look like. Close to the black hole, the mass of the particle is negligible compared to the curvature. And so you can just treat it as infalling massless scalars onto the horizon. And then there's some, if this alpha parameter is small, then those two regions, those two approximations are valid in some overlap region where you can match the solutions. And so the rate at which the particles get absorbed onto the black hole gives this imaginary energy. Yeah, great question. Okay. Right. So in this case, we're taking order 1 of the rotational energy of the black hole and putting it into these clouds of particles, axions or other light weakly coupled bosons, where a few percent of the black hole mass gets distributed over roughly tens of black hole radii in volume. So the energy density in these particles can be about the energy density of a neutron star. These are really pretty hefty objects, and they can give you some really interesting observables.
If you now have, okay, so you have like a fluctuation in black hole mass, so you have like an extra potential fluctuation, which is non-spherical.
Mm-hmm.
That will do something to the stars. So have you spun up some kind of kinetic theory in which you take account of resonances between the stars' orbital motion and its fluctuation?
Yeah, so you can look directly for the impact of the cloud on like the metric around the black hole and what observable effect that has. It is not very big because it's a few percent of the black hole mass, and it's not axisymmetric, but it's that higher order. So to leading order, it's pretty symmetric. And so effects on, for example, like stars orbiting the central black hole in our galaxy is not very large. Something you might hope to look for is if these objects are in LISA and you see, many orbits over time, and you can track that small change deviation from perfect symmetry. That would be something. But in principle, yeah, that's it. That's an interesting direction. So far, there's no kind of smoking gun signals. The effect is a bit small, but so right. So let's see how this happens with like some explicit numbers. So if new light particles exist, then fast spinning black holes will superradiate and lose their energy, mostly angular momentum, to exponentially growing bound states of these axion-like particles. So here I'm showing the black hole spin on the y-axis and the black hole mass on the x-axis in solar masses. And let's assume for reference, there's a new particle in the spectrum. It doesn't have to be in the vicinity of the black hole, just has to exist like in the Lagrangian description of our universe. There's this new particle that has mass 6 × 10⁻13 eV. If the black hole is born with a high enough spin to superradiate, then it will lose some angular momentum to inform this cloud of particles. So here I'm showing where the superradiance condition is satisfied in the blue region for bound states with angular momentum 1, 2, and 3. So in this case, a cloud with angular momentum 1 will grow. And in about a year, the black hole will lose order 1 of its angular momentum and a little bit of its mass. And then saturate the superradiance condition, because now the black hole and the particles are co-rotating at the same angular velocity, and you no longer extract any more energy. And here you've extracted about 10⁻77 particles, each one carrying an h bar of angular momentum, which gives you a total of 10⁻77 h bars if you calculate how much angular momentum is lost from the black hole. So if this is a process that stops the energy extraction, you get these huge numbers of particles in the cloud. Yes, this was it.
So what's the limit of the lower black hole mass here?
Yeah.
So for example, is a 5 solar mass black hole doable for this super radiance? And because that can be very relevant region for like the stellar mass black holes in the Milky Way. So I'm just curious.
Yeah, absolutely. Yeah, so here I've picked a particular mass. So the mass of the particle gives you kind of the overall scale of the problem. And then the most relevant parameter to how fast this processes happen is the ratio between the particle wavelength and the black hole size. So if you want to go to lighter black holes, you can go to, it will be sensitive to a heavier axion mass. And mostly all of the other things will remain unchanged if you keep that ratio fixed. So I'll show you later some constraints from stellar mass black holes that are relevant. But the reason that these curves turn over at the bottom here is because eventually, if the black hole mass is too light for a given particle mass, and that means the black hole is very small, and this cloud is very, very big and dilute, and it's not efficient at extracting energy from the black hole. So you will get, so it's not like the process isn't happening, it's just not happening on astrophysically relevant timescales that'll be taking millions or billions of years, and then you can't really say anything useful. So let's look at this again. So here I'm showing the number of axions and the black hole spin as a function of time. So over time, the number of axions will grow exponentially. So you get this really steep rise. The black hole will spin down. Most of the spin loss happens in the last e-fold, because that's when the largest mass transfer happens. And then over a longer time, these particles will actually deplete somewhat, because there is a non-zero energy density, which is time varying in this cloud, and that source is gravitational wave radiation, which carries away energy from the cloud. Over a longer time scale, the next level here, which has angular momentum 2, will start to grow. It's shown in dashed in this plot. So this is the occupation number of the next level of axions. It has a parametrically longer time scale because it has a bigger angular momentum barrier with less overlap with the horizon, giving you a smaller amount of dissipation. And notice that the two levels never exist at the same time, because once you start splitting down the black hole to form the angular momentum 2 level, here I'm using the hydrogen notation. So 2 and 1 is s orbital and so on. So once you go below this superradiance condition line for level 1, you see this guy drops all the way back into the black hole, because now instead of a positive superradiance rate, this level has a negative superradiance rate. So once you start growing the next level, the first one will get absorbed back into the black hole. And the black hole will take another kind of jump in the spin and the spin plane, which is shown on the bottom here. So as I mentioned, this period of time, you can get significant gravitational wave emission. In particle physics language, you can think of this as two axions annihilating into a graviton in the background of the black hole metric, which helps conserve momentum and energy at the same time, because it's not translationary invariant. Or you can just think of it as, you know, a large energy density that's rotating. So of course that emits gravitational wave radiation. And nicely for us, this time varying energy density sources coherent and monochromatic gravitational waves, because you have a very large classical source of these particles. This fits very well into searches of these mountains of neutron stars that LIGO and VIRGO do to look for kind of spin down of pulsars and gravitational waves. There are slight modifications that you need to make to these searches, but they are currently being done. And in principle, you could look for these in blind searches of black holes from the Milky Way or further away. And I'm happy to chat afterwards about more details of these searches, but we've proposed different ways of doing them. And I'm very excited that there's actually, you know, searches with real LIGO data that are currently being done to look for them. We haven't found anything, and LIGO and VIRGO haven't found anything. Otherwise, you probably would have heard about it. But you can either do monochromatic searches that are blind over the sky, assuming that you have some black hole somewhere that's emitting a signal, or you can do stochastic searches where there's some overlapping signals, and these are both being carried out. The issues with these searches is that we don't know what the distribution of black holes is in the Milky Way very well, especially we don't know their spin distribution. So in terms of setting actual constraints in particle parameter space, they're not very robust, because you need large amounts of highly spinning black holes to be able to produce these clouds.
What about the conditions on the actual axions being close to the black holes? Do you not need a certain minimal number to hang out there in the first place to initiate that? I mean, that is sounds like it's calculable, right? From the energy density.
Good. Yes, so that's a great question. And the answer is no, you don't need a particular initial density because this is actually just a classical instability of the black hole. So if you have any initial number of axions, which could even be the 1/2 h bar omega that's sitting, like the quantum fluctuation that's sitting in that level at all times, that'll get excited and grow the cloud to large numbers. So it's an exponential runaway process. So it's like an upside down pencil that's balanced. And if you have like a tiny quantum fluctuation, it'll fall over. So that's really great because you don't need to assume anything about dark matter abundance or what the messy environment of the black hole is. Even an isolated black hole with no particles around it will do this. Yeah.
But what about like supermassive black holes at the centers of galaxies? I mean, there you might have like a dark matter spike.
Yeah. I mean, yes, you can have initial conditions which have some particles around, but remember the final energy density of these things is going to be of order like a neutron star density. So you're never going to get that much dark matter, like there's just no comparison. So maybe you'll save a few e-folds at the beginning of the growth if you have some bound states exactly right, but the overlap of any kind of dark matter distribution with the right bound states is not that big anyway. So yeah, to get to the final energy density, you need about 200 e-folds of growth. And so if you have some density initially, maybe you'll cut out the first 10 or something.
Just like with the stars, it's not really a probe of dark matter, it's a probe of the light sector.
Exactly. Yeah,
Okay.
exactly. Yes. Okay, right. So just the last point is that I think the most exciting search for gravitational waves would be follow-ups to mergers, where you know that you have a rapidly rotating black hole that's been formed because you've captured most of the angular momentum of the binary, and you know roughly where it is, you know the mass and the spin to some extent. But these signals are much weaker than the merger signal, so we probably need to go to next generation detectors to be able to see these in the data. Good, so that's the story about gravitational waves or gravitationally interacting particles. But we have this very large parameter space, and the QCD axion in this region is very weakly interacting. But in principle, we want to understand what happens when, as was mentioned earlier, if you have some self-coupling of the cloud, that can change the dynamics. And we have these huge energy densities, right? So we have to worry about what would happen if you have some additional interaction between the particles. What new dynamics can arise if you have non-gravitational interactions between the particles, which are predicted by these models. And in particular, if you keep expanding around this potential that's generated for the axion, first order is quadratic, which is mass, and then you get usually a quartic interaction, which is some contact coupling between these particles. So far we've talked about superradiance, which is the black hole growing cloud of particles around it, say in bound state 211, and gravitational wave emission, where you have the energy density, which is quadratic in the field, so 2 powers of the field source a gravitational wave. But if we have self-interaction, you can get other processes. For example, you can get level pumping, where you have the first level that grew sourcing another level with a different amount of angular momentum. If you have level 211, you can take 2 particles in 211 and make 1 particle in 322. This conserves angular momentum. And then there's some extra leftover energy, which gets dumped into the black hole. If you calculate how much energy is left, it's still bound and it falls into the black hole. If you take now, once you've populated some energy density in 322, that you can get the reverse process where you take 2 particles in 322 and it goes to 2 and 1. Of course, it can go to other states as well, but this one is going to be boson enhanced by the large number of particles already in this level. And you'll have some extra leftover kinetic energy. So you'll have the 4th particle escape off to infinity as an axion wave.
Say that again, boson enhanced because there's a lot of particles already in that level.
Yes, so you have, so the rate, so the rate of this process is proportional to 3 powers of the axion number in these states. It's proportional to twice the number in 322 because they're in the initial state. And since these are bosons, there is boson enhancement in the final state. So the rate to put an extra particle in a state where there's already n bosons is n times the rate if there were only 1 particle. So it's like a laser.
Why do they care about? The whole point of bosons, they don't care about how many particles are.
No, they care. They like having more particles in the same state.
Well,
So it's like a laser. If you have already many many modes in the same state, the probability to get 1 more is enhanced.
Are you assuming any like special kind of self-interactions, or I missed that part?
This is just a quartic self-interaction. So it's just you're expanding the potential to next order, you have a mass, and then you have, if it's symmetric about the origin, you can do this analysis if it's cubic too, but basically you end up with the same conclusions.
But still no, like nothing with standard model.
Yeah, so this is just within the cloud. Yeah. Good. So, right, so just to give you a sense of why these processes might be important. So superradiance, the rate, the number, the rate of change of the number of particles is proportional to the mass times the number of particles with some coefficients that depend on the superradiance rate that are small. And then you have gravitational wave emission, which is proportional to twice the number of particles because that's the energy density of the field. And then you have, G Newton suppressed rate times the mass squared. Then for these higher rates, what you have is the core decoupling, which I'm calling lambda here squared, times the number of particles cubed. As I said, there's 2 in the initial state and 1 in the final state. And for typical axions, this core decoupling is of order the mass squared over FA squared. If you expand these cosine type potentials, that's what you get. And so this means that you have more powers of large occupation numbers if you go from left to right, but also more powers of small couplings where you add factors of the mass over some high scale. And that high scale is either in Planck or FA, but if FA is of order in Planck, then these are all kind of order the same. These rates can all compete with one another. So to put that a little more concretely, this plot is very busy, so let me just walk you through it. So here's the mass. This is the same plot I was showing for the axiom parameter space, zoomed in a bit. So here's the mass in electron volts on the x-axis of the axion, and here's the interaction scale F in GeV. So going to higher parts of this plot will give you larger interactions. So here's the QCD axion line for reference and the dark matter line for reference. And as you go from weak self-interactions to strong self-interactions, you get different types of dynamics which emerge in the cloud. So I'll talk about all of them, but basically in this bottom region, it's the story I already told you about gravitationally coupled particles. And then once you start turning up the self-interactions, you can have new effects like 2 levels being occupied at the same time. You can have gravitational wave transitions. At even larger self-interactions, you start to slow down the spin down of the black hole, and you can start to emit axion radiation. So just backing up before we had gravitational superradiance, where you had a black hole that spins down, and then the next level is formed, and the annihilations of axions are depleting this level. So that's what I showed before. So this is for axion that's gravitationally coupled to itself. If you go to more strongly self-interacting particles, what you get is you get an early growth of this next 322 level. So remember before I was telling you that you only have 1 level at a time because otherwise the superradiance of condition of any 1 level could be satisfied only at 1 at a time. But here now you have these, instead of the black hole sourcing the next level, you have the first cloud that grew being the source for the next one. So you can think of just like, electromagnetic currents source electromagnetic waves. Here, the coupling is such that axion energy density sources more axions. So you have the first level that grows in the solid line, grows through black hole superradiance, but then once it has large enough energy density, it starts to source the next level, which is shown in the dashed line here. And then they co-evolve by emitting axion and gravitational waves. And so you get new type of dynamics in the cloud. The one interesting thing in terms of signatures that happens here is since you have a non-trivial population of 2 different axions with 2 different energies, you can have gravitational wave transitions where just like in a hydrogen atom, you have an electron go from 1 level to the next and emit a photon. Here you can have an axion go from 1 level to the next and emit a graviton. And that is now going to be an energy level splitting instead of twice the axion mass energy. So it'll give you different signatures. So here you can have gravitational wave transitions between the levels. If you keep going to even larger self-interactions, so going at fixed axion mass, turning up the coupling, you can have new energy loss mechanisms. So as I was showing you before, you have these axions which can fall back into the black hole or be emitted to infinity. So in addition to the black hole pumping the cloud with more and more energy, now you have these extra sinks of energy loss. So if those are efficient enough, then what I'm showing here is the occupation number for different self-interactions. So you can see that this more you turn on the self-interactions, the lower the maximum occupation number becomes, because you're efficient just as you're trying to populate the cloud with more and more axions, they're being carried away in these axion waves. Since the occupation number is reduced, on the bottom right plot, I'm showing the spin down of the black hole. It's also going to be slowed down because with fewer axions in the cloud, the rate of energy extraction becomes smaller. So as you keep increasing the self-interactions, the spin down of the black hole will become, instead of tens of years, becomes thousands and even billions of years. And finally, if you have, oh yeah, that's what I said. So you have, as you increase self-interactions, you get a smaller axion cloud that scales as the self-interaction strength square and a longer black hole spin down.
So you don't change the dark matter line for the quartic self-interaction?
I don't change the dark matter what?
Like the abundance, I mean, that's like when you add this new interaction, that doesn't change the abundance, right? Like,
So this whole story is, as we were discussing, it doesn't care about the overall abundance. So then you care.
should the axion, like the dark matter line?
Yeah, exactly. So now, depending on where you are in this axion plane, you may think it's a more or less well-motivated model to look for, because if you're sitting here, then it could also be easily the dark matter. If you're sitting here, it could also be the axion. You're somewhere else, maybe it has nothing to do with either of those, but the black holes are there, so we might as well use them to look for it. Yeah, so depending on where you are, it will kind of more or less motivate this parameter space based on other considerations, but in terms of the black hole process itself, it doesn't care what's happening with the dark matter. Yeah. So since we have this black hole spin down, which is a function of the both the mass and the interaction scale of the particles, there's already been black holes masses and spins that have been measured both in LIGO and in X-ray binaries. These are measurements of masses and spins based on properties of accretion disks of black holes of different masses with the corresponding error bars. And you can see that for a pretty heavy particle, well, on the scales that I'm talking about, 10⁻11 eV, these black holes, which are, as someone was mentioning, are 5 to 10 solar masses, will exclude the presence of this particle, because these black holes should have spun down to the bottoms of these curves within a pretty fast time scale. So if you put this on the axion parameter space, these are some of these black holes whose spins have been measured. And some of the error bars are quite large, but you can use them to exclude parts of the parameter space. So in this range of axion masses, you would have spun down these black holes below their observed spins within the errors much faster than the projected age of the black hole. Once you go to stronger and stronger self-interactions, the rate of spin down decreases because the size of the cloud is limited by these self-interaction processes, and eventually you don't get a constraint anymore. But you can see that most of these more motivated particle parameter space is still covered by these constraints. There's also some new results from a group of LIGO folks who looked at some of the black holes that were observed in LIGO mergers. You need to look at the initial black holes because they need time to spin down. And so they constrain a factor of about 2 in axion mass down here as well, based on some rapidly spinning black holes. So there's a Salvo Vitali and Ken and others. I should add that to the slide. So there's a little, so you might say, okay, well, that's good. So we can say something about these very weakly interacting particles, which is very exciting because remember at the beginning, I was telling you most of the constraints that we currently have are coming from the top down. Of course, it's easier to look normally for particles that are more strongly coupled to us. And these are coming from the bottom up. So that's very interesting, but maybe there's nothing else we can say for these kind of moderately interacting particles. But that's not true. You still have this new process of axion wave emission. And so that's what I'll talk about in the last few minutes. So while you have no more strong gravitational signatures of this process, you have a new source of axions. So here I'm showing again the time evolution of axions as a function of time. So the blue line was for gravitationally interacting axions, and the orange line is for more strongly interacting particles. So like dark matter type level. Here you have a very long period where there's a quasi-equilibrium occupation number of these particles in the state, and you're constantly emitting axion waves. So the black hole is spinning up or is spinning down, is putting more energy density in the axion cloud, and the axion cloud is emitting axions. So this means that some fraction of the black hole energy is being slowly converted to axion waves. Just for like the gravitational waves, these axion waves are monochromatic and coherent, and they can be detected if axions couple to the standard model. So far I haven't assumed anything about whether these particles interact with our photons or our electrons or anything. This is a very general probe of new ultralight states. But if they do couple, then this is a new source of these particles that you can look for in the lab. And so this is this process where you have two particles, for example, being emitted, combining to make one bound state and one unbound state. So if these are the initial conditions, then the axions that are being emitted have velocity of about alpha over 6. Alpha, remember, is binding coupling, which you can think of as being between 10 to minus 2 and 0.5, depending on the parameters of the black hole mass and the particle mass. So in general, this is pretty fast compared to, say, the dark matter in our galaxy. Dark matter has velocity 10 to minus 3. This can be up to almost 0.1. So you have this flux of non-relativistic but relatively fast particles that are coming from these black holes. Luckily for us, people are already looking for these types of particles because we want to find axion dark matter. And in particular, at these frequencies that black holes emit, there are these proposals to look for axions coupled to spins. So it turns out that axions act on spins very similarly to how a magnetic field would act on spins. And so you can read out background axion as you would try to pick up a small magnetic field. And that you can do with techniques like NMR. And there are experiments, including something called Casper, that are being developed to look for axion dark matter. So if you try to look for these, what does the signal kind of morphology look like? It's very similar to what you would look for in the dark matter signal, except even better, because it's more coherent. It's just sourced by this huge energy density in the cloud sitting up next to the black hole, and it lasts for a very long time. Remember, I was showing you these signals that are, or these occupation numbers that stay basically dead constant for a billion years. So this signal could just be on from some black hole out there, like Cygnus X1. We know it's rapidly spinning. It's a few kiloparsecs away, and it could have a cloud of these particles that's constantly being pumped up by the black hole and is constantly sending out these axion waves out to infinity. So here is, I'm showing contours of the signal time, how long this axion wave signal will be on as a function of axion mass and coupling. And these are a log of the signal time in seconds. So you can see up here, it's longer than the age of the universe. So 10 to the 15, 10 to the 13 seconds. So if you see the signal, you can study it for a very long time. And that helps with experimental considerations as well. So if you look for These are just showing some experimental projections from different black holes. So here's Cygnus X1, here's some other ones, here's some hypothetical black holes that are close to us. Of course, if they're close to signals, they're going to be bigger. And these are some experimental projections. So on the y-axis is how strong the signal is as a function of axion mass. And above this, so some of these are but model dependent because you need to assume how strongly the axion couples to us. But the simple question to ask is, what is open parameter space for axion particles? And so this line with future reach of these detectors that are looking for dark matter would be able to see open parameter space for axions coupled to spins from all of these different black holes. So that's very exciting. It's a new signal that you can look for. And the detection side depends on the model, of course, but it's a new source of axion in the universe that you didn't have, that you wouldn't have without this black hole process. So in addition to having potentially dark matter production in the early universe and also stellar production of axion emission from thermal effects, this is another new way that you can populate the galaxy with axion waves and then potentially try to discover them in the lab. So with that, I will conclude. So we've talked about searches for axion-like particles in this parameter space, where black holes let us access a previously very difficult part of the mass and coupling parameter space. In particular, if these particles are very weakly coupled, almost Planck scale interactions, you can still look for them using black hole spin down and gravitational wave emission. If they're coupled a bit more strongly, then instead of gravitational waves, these objects will emit axion waves. And those you can actually also look for in the laboratory. So thanks very much for listening. I will take more questions.
Have any questions?
Can I ask a silly question? So you said that axions are there anyhow. Why you need them to gain energy to help the detection?
Maybe I misspoke. So there's in general, if you picture these bound states around the black hole, they're just kind of solutions of the equations. And in general, each mode will be populated with some on average quantum fluctuation, but that you can't measure. I mean, that's basically negligible. Each of these particles is billions of times lighter than billions of times lighter than, say, the electron. So it has no effect on anything. But then you have this exponential runaway process where now you multiply that by 10 to the 70, and now you have an energy density that's significant and can source, for example, gravitational waves that are still big enough to be observable on Earth, or axion waves that might potentially be observable on Earth. Or there might be other observables like we were briefly discussing, because there is a large amount of energy density in this cloud. So it could have other implications on, say, orbits or deviations from just black hole metric.
And do you expect this is a dominant channel for them to get energy?
Say that again?
This mechanism they talk about, do you think this is a dominant mechanism to pumping energy to axions?
Well, for these particular states, so there could be some background of axions that's just there because it was produced in the early universe, but locally around the black hole, yeah, this is by far, I mean, if this happens, then this will completely change the dynamics of the black hole. Yeah. Yes.
I was a bit confused about this continuous emission picture that you said. I mean, I would expect that to be like a step function. So you said like if it's
What's the step function?
Like the emission from black holes would be like I mean the black hole would spin down and then the emission would stop. So
yes,
I was a bit confused towards the end. Maybe I didn't pay attention. You were saying like you have this constant signal over a long period of time.
Yeah. So the difference is you're right that so here's the difference. So here's the number of axions. Is what I was saying before is you grow exponentially and then you extract enough of the black hole angular momentum that it stops, like what you said. And then eventually it kind of slowly peters out the occupation number goes down because it's being depleted by gravitational wave emission. But if you stop the growth earlier, then while the black hole still has a lot of spin, then it becomes kind of a quasi steady state process where you are inputting energy from black hole spin down, but at the same time carrying it away with axion wave emission. And so those two reach equilibrium, and you have this constant number of axions where you're inputting them from the black hole and outputting them by emission to infinity. But eventually, at very long times, over here, you see it starts turning over, and that's because the black hole eventually does spin down, and then this process stops. And so depending on the strength of the self-interaction, where this quasi-equilibrium is achieved will vary. So the stronger the self-interaction, the faster you're emitting axions from the cloud. So the smaller number of axions you need to have a balance between the black hole and the axion emission. If the self-interactions are not very efficient, then the first thing that's going to come in is the black hole spinning down. Does that make more sense?
Yeah.
Okay.
One other question I have is so if there's like some decay to standard model photons or something, can you maybe it's very hard to target like individual sources because the accretion disk may be already pretty bright.
Yeah. So standard model photons is difficult. So in principle, there is a process that could happen, which is parametric resonance. So just one axion going to two photons, like a single particle decay. For these masses, a single axion decay rate is, I think, 10 to 77 years. So you would get one axion from the cloud decaying to two photons within the whole age of the universe or whatever. So that's not very interesting. But you can have this other process where if you have an axion classical field that's oscillating and you have this coupling to two photons, then you can have kind of a parametric resonance process into the two photons where basically before, as the axion decays, before the photon escapes from the cloud, the next decay happens and then you get a runaway process. That's a rough picture. But for that, you need a very large E over F. So you need a large energy density of these particles. And typically if you plug in like typical values of the photon coupling, you're not going to get there because this process will kick in first. Because the self-coupling of the axions is related to, everything is set by the same scale, which is 1 over F. So unless you enhance the coupling to photons, I forget by what factor, but maybe 10 to the 5 or 10 to the 6 from the expectation, you're not going to get this process happening. And even if you do, it's not clear because these photons are kind of radio and there's a lot of stuff around the black hole. So they won't be very clean photons. So it's hard to do photon observations with axions clouds because you're not very efficient. And there's a lot of plasma around. These photons are going to be emitted at kind of sub-plasma wavelengths. So they're going to have a hard time getting out. There are some cool signatures that we've been thinking about if instead of axions, you have dark photon clouds. That's still in process, but I might mention it at the coffee tomorrow. So we talk more about it, or if you want to discuss. Yeah.
More questions, I guess.
There are a lot of interesting things that might happen with like a binary black hole collision. I think you mentioned that you wouldn't expect to see much impact on the gravitational waves, but I mean, for even for LIGO looking at stellar mass black holes, if you have this fuzzy envelope, would that impart a significant phase?
Yeah, so it's a great question, and so I thought a little bit about this, and there's also some nice work by actually Hornchen, who's here, and Dan Bauman and others on what happens when you have a binary. So the problem is that by the time you get to the LIGO band, if you want the signal to be big enough, there's two issues that you have to be worried about. One is that the cloud will have gone away already due to gravitational wave emission, because if you want the cloud to have a lot of mass and be very compact, so it gives you a big difference to your in-spiral signal. That also means that the gravitational wave power is large. So it will have already depleted by the time you're close enough to be in the LIGO band. And the other issue, which is what this other group has looked at, is that you will start to disturb the cloud itself, right? So all of this was for an isolated black hole where you're dominated by the potential of the black hole. But now if you introduce a perturbation that's not axially symmetric, you can start to mix different levels of the axion. So for example, you start with an axion with angular momentum 1, now you can change it because you have this new perturbation, just like in a hydrogen atom, like with a magnetic field, you can add an admixture of angular momentum -1, and that one's going to start falling into the black hole, or you can get oscillations between different levels. So typically, by the time you get to the LIGO band, you're going to have destroyed the cloud either through gravitational emission or through tidal effects and these kind of resonance processes. That's why I mentioned LISA, because at that point, they're far enough away that if you have enough precision with many, many orbits, you could tease out the effect of the cloud maybe, but you won't disrupt it yet. But I think that's still kind of work in progress. Like there's no conclusion on which parts of parameter space you can be sensitive to and which ones you can't. Yeah.
Do you have any questions from Zoom? No? More questions from the audience? Okay, if not, let's thank Masha again.